Hello, welcome to this video where we're doing as the title says. It's a very short basic introduction to how to solve series circuit problems using the equation from Ohm's law. And if you're watching this, it's probably because you have been asked to work through what I've named worksheet A of some simple series circuit problems. And so what I'm going to do is I'm going to go over each of the exercises in the left-hand column, and that will leave you with sufficient understanding and confidence to be able to do the right-hand column. So this is the first question, and underneath the circuit I've written V equals IR form of Ohm's law, and you should already know the symbols that V is for voltage, I is for current, and R is for the resistance. So if we look at our circuit, if we want to get some information about what the value of I would be, we would have to look at ammeters. If we wanted to know what values of R would be, we would have to find resistors in the circuit diagram. And finally, if we wanted to know what values for V would be, we would have to look for voltmeters, and you can see that the voltmeter there is connected as it should be in parallel across the component. I've written V equals IR again because now I want to understand which of the variables I have and which I don't. So I have an ammeter reading of 2 amps, so I know what my value of I is going to be. I have a resistor with a value of 5 ohms, so I know what my value of R is going to be. And I know that I don't need to rearrange this equation, then I can go for a straightforward substitution to find my unknown, which is V. I've written that out again at the top now then to do the substitution, and I've also top and tailed the I to make it distinct from a number 1. So V equals IR, simple substitution, V equals 2 times 5, and therefore my answer, which you won't get right if you don't include the unit, is V equals 10 volts with a capital V. So that's the first task. Second task in the left-hand column, starting out the same way again. I've written out my V equals IR to look at what I've got. I've got a reading for a voltmeter. I've got a reading for a resistance, but I don't know what my current is. So I'm going to have to do a rearrange now to make I the subject of the equation. So rearranging that equation is going to give me I equals V divided by R. Writing it out again, making my I clear, I equals V over R, and I substitute in. So I'm going to have 10 for my voltage divided by 4 for my resistance, and that means again I've got to include the unit. My answer will be I is equal to 2.5 amps. So the reading of that current on that ammeter is going to be 2.5 amps. And the third and final example, working again in exactly the same way. Let's look at what we have. So I've got a reading for a voltage, I've got a reading on an ammeter, but I don't know the resistance this time. So I'm going to have to make R the subject to the equation and rearrange as so. So R equals V over I. I'll rewrite that again and now substitute in. So I'm going to have 7 divided by 4, and that's going to be an answer which you must include the omega because it's a resistance value of R equals 1.75 ohms. So you should now have enough to be able to tackle the right hand side of the equation. There's a little bit of an extra level of demand on you, and that is that you also need to appreciate rules for series circuits, but we're going really easy at the moment, so the only thing you need to be mindful of is number 1, and that is wherever you place the ammeter in the series circuit, you're going to have the same reading. So good luck with that. Thanks for watching. Bye bye. Hello. Now in this video we're going to look at some more demanding series circuit problems, and to solve those not only will we have to make a lot of use of Ohm's law, but we will have to make use of the rules for series circuits as well, and you should have met those in the video you were asked to watch beforehand. So let's just have a reminder. So the rules for series circuits are no particular order, but the current is the same wherever it's measured in the circuit, And if you watched the previous video that I did, I just put that A1 equals A2 equals A3 because that was starting out on a beginner's guide to solving those problems, and I was more concerned with looking at the readings on the ammeter. But if we're going to write these down as notes, which we are, then really we should write that I1 equals I2 equals I3. Second rule, the total potential difference, the voltage, is divided between all the components, but not necessarily equally, as you probably know by now. That depends on the resistance of the components. So VT, as the total voltage across the circuit, is the sum of V1 plus V2 plus V3, etc., etc. The third and final rule is that the total resistance of the circuit is simply the sum of all the individual resistances. So the total resistance RT is equal to the individual values R1 plus R2 plus R3, etc., etc., etc. So if you can make a note of those in your book, that would be a good start. Now, this is not essential, but it's just that I've gotten into a way of working which is that I want to be thinking more about the problem than continue to rearrange Ohm's law. So I always think it's a good idea that I write out Ohm's law with each of the parts as the subject of that equation. So we've got V equals IR, I equals V over R, and R equals V over I. But that's just my way of working. It's entirely up to you whether you do that. As you can see, here's our first problem, and for ease of explaining things, I've also popped those two rules, or the rules and the set of equations, up in the top right hand corner. In this circuit then, let's have an analysis of it. What do I know? So if I write down V, I and R, let's look at those in order. So looking at voltage, what do I know about that? Well, nothing. I don't know what the total voltage across the circuit is, and I don't know what the individual voltmeter readings across each of those resistors is. Current, yep, I know that. So that's given me a current on that ammeter of 0.2 amps. So I'm fine there. And my resistance. Well, I know the individual resistors, and so it shouldn't be too much of an issue knowing the third rule to find the total resistance for the circuit. So I also know that 8 plus 12 would equal 20, so the total resistance is 20, so that might be useful, but that's okay. So I've only got one variable to find, so let's have a look how we do that. And first inspection says, well, I could go ahead and do that 8 plus 12 equals 20, and then I could put everything into V equals IR, and I could get a value for V. But there's a slight problem with that, because that gives me V1, but it doesn't tell me anything about V2 or V3. So I'm going to do this a different way. And what I'm going to do is I'm going to solve for V2 and V3, because I know that the total VT across the circuit is also the reading that's on V1. So I know that V1 equals VT. That's right, yeah, V1 equals VT. It equals V2 plus V3. So if I solve for that, I've got everything I need. I can solve for V2 because, as I've highlighted at the top there from our first rule, we know that the current running through those resistors is identical. It's a series circuit. Wherever you measure the current, it's the same. So I've got 0.2 amps running through the 8 ohm resistor. I've got 0.2 amps running through the 12 ohm resistor. So for solving my V2, I've got V2 equals IR, and I know those values. They are 0.2 and my resistance is 8. So my V2 is 1.6 volts. I can then go on to solve for V3 in the same way. So I've got 2.4 volts as my answer there. If I add them together, that means my reading on V1 is going to be 4 volts. Now, if I wanted, I could go back and use that idea of adding the 8 and 12 ohm resistors together and solving for the whole circuit just as a double check. So let's try that. Rule 3, 8 plus 12 gives me 20 ohms. V1's going to be equal to the current times the total. I've used V1 because, so total resistance, I've used V1 because that's also equal to VT, that's for the whole circuit. All of these values are now for the whole circuit. So V1 is going to be equal to 0.2 times 20, and that is 4 volts. And that agrees with the answer that we got before. So that's how to do that particular problem. I'll see you in the next video. Thank you. Bye-bye. Here's a next problem in more challenging problems for series circuits. We'll do an analysis of that, but first of all, I'll just pop those rules and rearrange formulae up there in the top right hand corner. Let's see what we have this time. So thinking about what we have in terms of our variables. On first inspection, if we look at voltage, we've got the voltage for the individual voltmeters across the resistors, but we don't have a reading on V1. However, that actually isn't a problem because we know from second rule that if we add 15 and 6 together, that will give us the reading on V1. So we actually do have everything we need to know about the voltage. Well, what about the current? Well, we don't know anything about that at all. And the resistances, well, we know one, but we don't know the other. So at the moment, we've got a bit of a problem because we've got, out of the 3 variables, we've got 2 unknowns. Up in the top right-hand corner, I've circled the rearranged formulae. I need to find some combination of variables that are going to allow me to work with one of those formula. And it's here. So I've got 6 volts and I've got 15 ohms. That gives me V and R, so I can solve for I. And if I do that, that's going to give me the reading on A1. But because it's a series circuit, because our rule for a series circuit, our rule 1 says the current's the same everywhere, it's going to give me the reading for A2. So I'll carry on and solve this. I equals V over R. That means I've got 6 over 15. So my current is 0.4 amps. So my reading on those ammeters, both A1 and A2, will be 0.4 amps. Let's pop them on the diagram. Now, because I know the current flowing through those resistors, I can solve for R1, because I know that through R1 there's going to be a current of 0.4 amps. And I already know how much is needed to be done to move that current through that resistor. So I've got 15 volts. Solving for using my R equals V over I equation gives me that R1 will be 15 from 15 volts, and I've got 0.4 amps running through it. So my value of R1 as resistor is going to be 15 divided by 0.4. Means R1 is going to be 37.5 ohms. So let's write that in there. And that only gives me one more thing to solve. So V1 is what's needed, and we already know that we can get that simply by adding, because V1 is the total across the circuit, simply by adding 15 and 6. And so my final answer here is 21 volts. So I'll just clear the board. And again, if I wanted to, I could double check my workings using values for the whole circuit. I know that the current flowing through the whole circuit is 0.4 amps. I know that the voltage across the whole circuit, the PD across the whole circuit, is 21 volts. And so I now need to use rule 3, that the total resistance of the circuit is equal to this would be 37.5 plus 15. So that's going to give me a total resistance of 52.5 ohms. And if I substitute that into V equals IR, that's going to tell me that 0.4 times 52.5 does indeed equals 21 volts. So that's a nice way just to check, and that's how you would solve that problem. Thanks for watching. Bye bye.